Hey scholars, welcome to the last section of chapter 19, looking at 19.4. How have we depleted the ozone in the stratosphere and what can we do about it? Because that is obviously hurting the environment as well, and has some effect on climate as well and global climate change. So we're going to take a look at that today. First of all, our use of certain chemicals have threatened the ozone layer. And basically what's happening is the ozone is actually breaking down. It's going from O3 to O2, which is oxygen in the atmosphere is diatomic element, except for when it's O3 that becomes ozone, which protects us from UV radiation. So it's happening seasonally, mostly in the Antarctic and the Arctic. It's happening in the stratosphere. That's where the ozone layer is kept. In 1930, Midgley was the first guy to actually discover CFCs, and we've used them many a times, and we've used them a lot in what we call freons. They've been used in aerosol spray cans, cleaners for electronic parts, refrigerators. We've used them a lot for everything. But Midgley is the first one to discover those and implement those into products. But in 1984, Rowland and Molina were the first ones to actually discover that CFCs themselves were the cause of depleting the ozone layer. And there are also other ozone depleting chemicals, not just CFCs. There are lots of other products like halons and hydrobromide fluorocarbons, or HBFCs, those used in fire extinguishers, methyl bromide used in fumigation for pesticides, hydrogen chloride emitted into the stratosphere by space shuttles. There's lots of cleaning solvents as well that have things that might deplete the ozone layer. But we found that CFCs were the major cause. This is just looking at the global average ozone values. We measure them in Dobson units, and later you're going to do a little lab activity that's going to be taking Dobson units and graphing this very similarly. But you can see from 1980, it's increasingly going down all the way to 2000, and about 2000 it started getting a little bit better and kind of evening out. But it's still not to where it was back in the 80s. So we've seen that a decrease in ozone, the thickness of the ozone. Dobson units is like the thickness of the layer. And there's an image kind of showing you total ozone in Dobson units, obviously nice and green and on the middle, but around the poles there's a very thinning. And I'm going to put a video down below this one that talks about why is it happening over the Arctic and Antarctic. It has a lot to do with wind patterns and taking those CFCs and circuiting them toward the poles. So I'm going to let you watch that on your own. But has been research in Rowland and Molina. Were very persistent and courageous in finding that CFCs were persistent in the atmosphere as well. They rise in the stratosphere over about between 11 and 20 years. It takes that long to get there, and also breaks down under high UV light, which is provided by the sun. And halogens produced accelerate the breakdown of O3 to O2, which is a bad thing because that is not ozone. It turns into pure oxygen. Each CFC molecule can last, though, its persistence in the atmosphere between 65 and 385 years. So it's not a chemical that goes away easily. In 1988, DuPont, little case study there, stopped producing CFCs, which DuPont at the time was a major manufacturer of products that contain CFCs and freons. And in 1995, Rowland and Moline were awarded the Nobel Prize in Chemistry. Actually, it is Moline. It's not Moline. Sorry. So Rowland and Molina were awarded the Nobel Prize in Chemistry for their hard work in figuring out that CFCs were the major cause of depletion of the ozone. This is just a kind of a chemical example. It shows you kind of a breakdown of how it works. The sun provides UV radiation, and the CFCl is the chlorofluorocarbon. When that combines, it actually breaks apart and produces a Cl by itself, a chlorine molecule, but it does leave CFCl2 by itself. So that's what happens. That's the first step. But then what happens in the atmosphere, when it's up in the stratosphere, the Cl binds to one of the O3 molecules, and it's added to it, and it causes a Cl. It causes one of those oxygens basically to take away from the O3 molecule and attach to the chlorine molecule and become ClO, or was that chlorine oxide? And then what happens is, plus that, then it has still your O2, which is really just oxygen gas. Not a bad byproduct there. Eventually, this happens over and over and over again. And that Cl eventually breaks off of the O, and the O is then released. So that's kind of it's a consistent pattern, and that's how it works. But the video does a better job of explaining it more than me. So take a look at that video. Why should we worry about ozone depletion in general? Well, first of all, if you don't have any protection from ozone, there are UVA and UVB wavelengths that are coming down from the sun, and that increases eye cataracts and skin cancer. It also is too strong and could impair or destroy phytoplankton, which phytoplankton usually use those rays to produce photosynthesis and take carbon out of the atmosphere. But if they are too strong and they impair or destroy that plankton, that also destroys that photosynthetic process of it. So here's some effects of ozone depletion. One of them is worsened sunburns as far as human health goes, more eye cataracts, more skin cancers, immune system problems as well. With food and forests, it reduces yields of some crops, reduces seafood supplies if phytoplankton has been reduced because of too strong of UV radiation, and decreased forest productivity and UV-sensitive trees. For wildlife, it also can cause cataracts in animals, decrease populations of aquatic species that are sensitive to radiation, like the phytoplankton, reduce populations of phytoplankton, and disrupt the whole food web of aquatics. Air pollution materials also will increase acid deposition or rain, increase photochemical smog, and degradation of outdoor paints and plastics, which then just cause more problems. And global warming, obviously, while in the troposphere, CFCs act as a greenhouse gas. So they not only deplete the ozone layer, they also act as a greenhouse gas. They're kind of a double threat in destruction as far as atmospheric climate conditions are concerned. All right, so here's a little focus on skin cancer. There are three major types: squamous cell carcinoma, basal cell carcinoma, and then melanoma. And most of those are taking place because of UVB radiation, and that's usually what tanning salons use, which is why they always say, hey, be careful what you're tanning. So this is the long wavelength. This is ultraviolet A or UVA, formed from causing aging of the skin, tanning, and sometimes sunburns, and it penetrates deep and also may contribute to skin cancer. You can see the different types of cells. There's this basal cell layer, squamous cell layer, and then melanocytes, which is where the melanoma can take place. So UVB is a shorter wavelength, higher energy form. Premature aging and wrinkling, it's largely responsible for basal and squamous cell carcinomas and plays a role in malignant melanoma. And again, that is the UVB light that's coming out of those tanning beds. This is just a look at what they look like. Squamous cell carcinoma arises from that upper layer of epidermis, that's that top layer of skin. And this cancer also is caused by exposure to sunlight or tanning lamps. It is usually curable if treated early, but it can grow faster than basal cell carcinoma, and can spread to other parts of the body. Basal cell is actually what my dad had it very similar on his nose. And if you tell me what type of cancer my dad had, as far as on skin cancer, I'll give you an extra credit point. First person to do that from each class will get one of those. So basal cell carcinoma is what he had right on his nose. Most common skin malignancy usually is caused by exposure to sunlight or tanning lamps. It develops slowly. It rarely metastasizes, which means jumps or spreads to different cells, and is nearly 100% curable if diagnosed early. And he had that part of his skin removed, or his nose removed, very small part. You can't really even tell. Maybe a very small scar. And now he's fine. So that's one. Now the worst kind is melanoma. It's the deadliest form of cancer. It involves with the melanocytes, which I kind of pointed out to are right there in that basal layer, which can produce this produces pigment, which is why they look darker. It can develop it from a mole or on blemished skin. Grows quickly, can spread other parts, which means metastasizes, can jump from cell to cell in different parts of the body, and usually that looks dark. So that's what melanoma is. Very, very scary. So what can you do? Stay out of the sun, especially between 10 a.m. and 3 p.m. And if you do, wear some suntan lotion. Do not use tanning parlors or the tanning beds. When in the sun, wear protective clothing and sunglasses to protect against UVA and UVB radiation. Be aware of overcast skies that only protect you. They feel like they do, but they really don't. There's still UV radiation coming through there. Don't expose yourself to the sun if you are taking antibiotics or birth control pills. That can cause some problems as well. When in the sun, use sunscreen, at least 15, SPF 15 or greater, and examine your skin and scalp at least once a month for moles or warts that change in size, shape, colors, and sensitivity. So that is another one that you need to do. Keep aware of your body. That's very, very important. We can reverse stratospheric ozone depletion by stopping producing all ozone-depleting chemicals. It will take 60 to 100 years to recover, of ozone layer to recover and rebuild itself. And in 1987 was one of our first major strides to do that. It said 87 representatives of 36 nations met in Montreal, Canada, and developed what we call the Montreal Protocol. The treaty's goal was to cut emissions of CFCs, but no other ozone-depleting chemical, by about 35% between 1989 and 2000. After hearing about more bad news about seasonal ozone thinning over Antarctica in 1989, representatives of 93 countries met in London in 1990 and then in Copenhagen in Denmark in 92, and they adopted the Copenhagen Protocol, which amended that accelerated and phased out the key ozone-depleting chemicals. These landmark international agreements, now signed by 191 countries, are important examples of global cooperation in response to a serious global environmental problem. So those are two good ones that a lot of people came together after. A few countries came together and really ratified and helped prevent further ozone depletion. We have substitutes available now for CFCs. A lot of you look at your aerosol cans, your hairspray cans, even in refrigerators, do not use CFCs anymore. They use an alternative, a substitute, and even more are being developed as well. Your book gives you examples of different ones, like most widely used substitute is HCFC 22, which causes some ozone depletion. They're trying to even make a better substitute for that might even be able to eliminate all of the CFC components in there as well. So those are a few of them, and that brings us to the end of section 19, chapter 19, and we'll see you guys next week for, I believe, non-renewable and renewable energy. See you guys next time.